Okay, why don't we get started? So today we're going to spend about half the time on the final part of the linear model and going to use other half of today's meeting to open it up for questions. As we said last class meeting on Thursday, we have an exam, written exam number 1, and it'll be on all the material up to and including bias and variance, which is what we covered on Thursday. So I'll end this at about the halfway point and just open it up for any questions you have about the material or the exam. Um, it will be a closed book, closed notes exam, and I will ask you questions that are a lot easier than what you'd have on homework because you don't have all your resources with you, and so everything will be fair game up to and including Thursday, which is bias and variance. Okay, all right. Um, so why don't we continue? So last time we talked about bias and variance, and we started out with an expression for out of sample error, and we did that double expectation with respect to data sets and with respect to inputs, and we use a squared error loss between our final best hypothesis G and the unknown ground truth target function F, and we carried that through uh, uh, some manipulations, and we came up with an expression for bias and variance. And so conceptually, we took a look at what bias and variance is, and we had introduced in that derivations the notion of a G bar, our average best hypothesis. And so we said bias is a measure of the descriptiveness of a particular hypothesis set. And this bias is the difference between our G bar, our average final best hypothesis, and our ground truth target function F. Um, and in this case, we said that if our hypothesis set is small or relatively simple or non-complex, we generally will have a higher bias, right, and a lower variance. But if our hypothesis set is quite large, we might have a smaller bias, and therefore the average best hypothesis G bar is closer to our ground truth target function, but it's going to vary from one instantiation of a data set and even one instantiation of an algorithm to the next. Because you saw in your homeworks that if you initialize differently the starting place in a hypothesis set and run something like PLA, you're going to have different results from one instance to the next based on where you start. And so here we have larger variance. This variance is this red region, but our bias is smaller. And so we discussed the point that if you're going to select a good hypothesis, akin to doing complexity analysis using the VC bound, this bias variance decomposition is a competing framework for how you choose this notion of a best hypothesis. And we saw that play out when we were looking at function approximation for the sine wave, and we had two hypotheses, the constant hypothesis and the line on the plane. And we saw that the constant hypothesis had a smaller bias and variance when we actually did out this example. All right, any questions about this? No? All right. So let's jump in and kind of a little bit of a revisiting, if you will. We talked about linear classification, and in doing that, we talked about the PLA algorithm, and then we made an improvement to PLA using the pocket. And then we changed our model a little bit where our class labels were real valued instead of just the +1, a -1, and we used that with the squared error loss to define linear regression. So here we take the same linear model with making a little bit of change to the labels as well as to the loss function, the expression that we use for in-sample error. We can use pseudo-inverse to solve for the best weight vector W in matrix vector form that gives us the best ground truth target function. And moreover, we tied these two together, linear regression and classification, by using the regression weights as a kind of bootstrap starting place within the set of hypotheses, and then running PLA on that. And that's something you can absolutely do and get an improvement. So now we're going to introduce another linear model to complete our discussion on these basic linear models. And this is to point out the fact that while linear models are very simple, all right, that's on purpose, by making some interesting, minor, relatively small modifications here and there to this very weak, very simple model, you can get it to do some pretty compelling things. Right? So this is logistic regression, and logistic regression is going to be based on this idea of a nonlinear transformation. Now, we talked about this idea called a phi function, and we had a diagram like this, and we started out with some vector valued representation in d dimensions. And because we're talking about models here, we augmented that input vector to be d plus 1 total dimensions through some phi function. Now, when we call this phi function on our input representation x in d plus 1 dimensions, we get some alternate representation in so-called feature space or z space. And this z space has a different dimensionality that they've been carrying in the book and we've been carrying in lectures as being d tilde. Now, d tilde can be a larger dimensionality than d, and that is certainly the case. And in doing so, that's called an expansive mapping. And so our transformation is typically expansive when you go from this d plus 1 dimensional input representation that's augmented with x naught to this d tilde plus 1 dimensional input representation. Now, the converse could actually be true. You could have a feature function or a phi function that is a so-called contractive mapping, where it does the converse, where the dimensionality d tilde is actually smaller than the original input representation d. That's absolutely possible. But in general, when you get these nonlinear transformations, to take advantage of nonlinearity, but you only pay the cost in z-space of training a linear model, typically it's an expansive mapping where this phi is a nonlinear function. Okay, so typically each of the features in z-space is some function phi sub I of some subset of the original features in the original input representation. And so this bank of phi functions, or this phi, is going to take on a set, or is implemented as a set of individual feature level phi functions, where that phi sub I can draw from any element of the power set among the features in the augmented d plus 1 dimensional vector in x space. Does that make sense? And so you could actually construct an arbitrary phi function. It doesn't matter, but the dimensionality of this z space, you're going to have d. You're going to have d tilde plus 1 many of these individual feature level phi functions. And so for each x, we're going to have a corresponding z. And here's an example of one such transformation. And so what this particular transformation does, suppose you have an input in 2 dimensions, so you have 2 features, x1 and x2 in your original representation. You augment it with an x naught, and the equivalent result of computing your phi function is to go from that 3-dimensional input representation to a 6-dimensional model representation. And so in this case, if we had the original feature vector was 2 dimensions, you augment it to make 3 dimensions, x0, x1, and x2, and then your z transform would have the first feature, or the 0th feature, would be 1, and then we have the x1, x2, x1 times x2, x1 squared, x2 squared. And that's a quadratic transformation, and a quadratic is certainly nonlinear. And so in that particular case, we're going from a 3-dimensional model to a 6-dimensional representation in our feature space. And what that tends to do in general is that changes the geometry of your feature space when you transform it. In this particular transformation, it's an expansive transformation, right? So the points are going to reconfigure themselves, i.e. the geometry changes. And so our hypothesis in our original representation, when we do the training, the PLA, update in Z space, if we were to map through inverse mapping what that means back in X space, that's going to be a nonlinear boundary in the original input representation. But we can still run a classifier with this by taking some new input out of sample, X. We run our phi function on that out of sample point X, and then we perform our sign W transpose on phi of X, where our W vector is W tilde in D tilde plus 1 many dimensions. Does that make sense? Yes. Yes, it's getting to logistic regression, but now we're just motivating it using nonlinear transformation. So that's one type of nonlinear transformation that we can make. Now, certainly one of the issues, if we talk about complexity here, we said and we developed when we looked at all of that stuff related to the VC bound, that we said the VC dimension is equal to a number of dimensions plus 1. Right, in our original input representation. So DVC in our original input representation is D plus 1. And we essentially count the effective degrees of freedom, and all things being equal, if there is no loss in the effective number of degrees of freedom, for each of these inputs X, each of our features, we're going to have a corresponding W, and therefore for D plus 1 dimensional input vector augmented, we're going to have D plus 1 parameters for the linear model. And when we transform this into the new representation, our VC dimension is going to be, and this is on purpose, less than equal to D tilde plus 1. And the reason for that has to do with the way we do these mappings. So you can imagine two different points from our original input representation. Let's say the first point, x1, and a vector valued, and the second point from our X representation, our original input representation, they could each have a different class label, say +1 and -1. But it could happen that when you perform that nonlinear transformation might map two different X vectors onto the same Z vector. And so if that's the case, well, certainly if you're trying to produce all 2 to the DVC many dichotomies in Z space, that becomes really hard to do if 2 original input vectors are mapped to the same exact Z vector in feature space. And so for that reason, this inequality here, DVC, in the transformed version of feature space, it's less than equal to D tilde plus 1. Right? Now you get equality if each one of these mappings into feature space is unique, and you get something that's less than D tilde plus 1 if it's non-unique mapping. Does that make sense? So there's a little bit of a conundrum here when it talks about the VC dimension in the transformed representation, because you could make it impossible if this mapping, this phi function, is not one-to-one. Okay? All right, any questions about this? All right, so what does this have to do with anything? Now, of course, when we make that mapping from original input representation to feature space, we can achieve a nonlinear boundary. And so in this particular figure on the left-hand side, upper left, we have a two-dimensional input representation. So you take this two-dimensional x1 is the feature along the horizontal axis, x2 is the feature along the vertical axis. Again, you'd augment this with x0 to make a model vector that is of dimensionality 3. But the original input representation has 2 features. Now, if you look at these points here, you'll notice you have 2 different points, so it's a +1, -1 binary classification problem. We have our red X's, which are mostly on the lower right, left-hand corner of this feature space. And then you have the blue circles, which are primarily on the upper right-hand triangle of this feature space. But you do have 2 outliers here. You have a red X that ground truth is deep within the blue territory, right? And you also have a blue circle that's deep within the red territory. And so certainly, if you look at the geometry of the data in our original input representation, they're certainly nonlinear, right? You can't really find a straight line that will separate these data points consistent with the ground truth target function, because out of sample, the ground truth target function corresponds to this blue region here. The blue shaded region is ground truth for all of the blue circle points, and likewise the red shaded region is ground truth out of sample for all of the red points. Does that make sense? And so the thing to notice here is that with this straight line, this linear model in the original input representation, we mostly have the classification correct, except there are just a small handful of points that are incorrect, right, relative to that final best hypothesis, namely that line, that linear model depicted in the figure. And so you can think of this as being mildly nonlinear, right? It's nonlinear technically in its geometry, the arrangement of points, but it's only slightly so or mildly so, right? And so the result of using a high dimensional expansive mapping phi function, right? If you take that resulting linear model in that z space achieved by a nonlinear mapping in a higher dimension d tilde, and then you map that phi function back to the original representation, if you have a higher order nonlinear transformation, maybe a fourth order or a fifth order or what have you, the resulting decision boundary, if you were to draw that in the original input representation, it would look something like this, right? You have this very complex nonlinear boundaries. Now, of course, when you go up in complexity of the representation, you also go up in the VC dimension, right? And so we said at the outset when we talked about the VC bound is how you pay for that increase in VC dimension is by having enough data points to be able to pay for it, right? And so this was evident in the modified version of Hoeffding's inequality that we arrived upon when we constructed the VC bound. Now, of course, here, we're not really changing the number of data points. We're just going up in complexity achieved through some nonlinear mapping, i.e. some very complex, expansive phi function. Does that make sense? So the difference between the two. But this problem on the left-hand side, with that result, some of the decisions you might make is if your model is only mildly nonlinearly separable, it might be better to take the original linear model in X space and just accept the fact that in-sample error is going to be greater than 0, right? Because as you can see here, if you pursued a highly nonlinear phi function, absolutely you could get En to be 0 in some high dimensional space, but the problem is you're going to get bad generalization, right? Because you can't get around VC bound, even when you do it non-linearly in a more complex feature space, because how you pay for that is with this W tilde, this increased number of parameters. And we saw that the VC dimension in that Z space, or that you effectively have when you make this highly nonlinear transformation into Z space, DVC is going to be less than equal to D tilde plus 1. Right? So if you go up really high in the nonlinear mapping, you're still going to have to pay for that complexity in the VC bound. And if you're not increasing the number of examples, you're going to get poor generalization out of sample. Does that make sense? So even though you can get nonlinear decision boundaries by paying the cost algorithmically of something simple linear model like a PLA search, you still can't get around the VC bound, right? Okay, so let's take a look at other problems. And this problem is different. This problem is not mildly nonlinear. You could think of it as being very heavily nonlinear, right? In the previous slide, we saw that for the most part, save a few handful of points, everything was linearly separable, right? It was only mildly nonlinear. And so in that case, if it's mildly nonlinear, it's better to accept the fact that in-sample error is going to be non-zero and just go with the lesser complexity model. But in the case where something is very strongly nonlinear, like this problem, the basic geometry here is that, if you were to take a straight line and try to separate these data points, the blue points from the red points in the original input representation, you're going to get something that looks close to half of the points wrong, right? So that's very strongly nonlinear. Now, certainly you could construct a mapping, a phi function that effectively achieves a polar transformation and get a very good separation in that resulting z space. So let's take that same mapping here, going from a three-dimensional model, x0, x1, x2, in this case, to a six-dimensional model using a quadratic nonlinear transformation for our phi function. So we have the same transformation to z space, right, in 6 dimensions. So we have the square terms of each feature, we have one, we have the individual features, and then we have the cross term, feature 1 times feature 2. Now, you might see this and say, gosh, well, I know if I go up from 3 dimensions to 6 dimensions, I need more data points. So you might decide, okay, well, let me kind of trick out VC dimension and try to get a discount on my complexity by collapsing this transformation to see if I can get efficiency for free effectively. So what could you do? Well, you could make the observation by studying the original input data and say, if I look at the origin, imagine some coordinates here going horizontally and vertically, the blue points tend to be closer to the origin and the red points tend to be further away from origin. So let me take this transformation and I'll just make the observation that I really only need these square terms and that 1 and reduce it down to 3, right? And you could absolutely try to do that and perhaps get away with it. Well, you can, right? But there's a caveat here. And you could even go further, right? Why stop there? You could say, okay, well, I don't need these square terms to be separate because I don't really care about whether you're talking about the projection along the horizontal axis or the vertical axis. You could combine those square terms and just make it now a contractive mapping in the z space, right? And call it 1, and the next feature is x1 squared plus x2 squared, right? Now you could even go further, and that would, you could absolutely do that. Now that I've noticed that, I can make another observation. I don't even need that one term. I can kind of combine them and just have a single feature representing my input representation. Now, you could think to do that and celebrate and say, gosh, well, I now have a VC dimension where my d tilde, it went from 6 down to 3, down to 2, and down to 1, and now everything's great. I've gotten this discount as far as the VC bound and complexity is concerned. And you would be wrong, because essentially what you're doing is you're doing what's called, you're basically taking the role of what the learning algorithm is doing. You're examining your data, and then based on that data, you're deciding which set of hypotheses to choose. And so in the first case, well, you considered a more complex set of hypotheses. And then when you made that observation from the data about the polar arrangement radially from the origin in the original representation, you're now reducing your hypothesis set down to something smaller and smaller and smaller. So essentially what you're doing when you do that, yeah, you can make that transformation, you can whatever you want it to be, but because you've examined the data in terms of the VC dimension, the complexity that you pay really isn't the final complexity of that last form of our Z transformation. It's the original, because in your head, you're actually doing some of that work. And so you can't get around that complexity. If you want to do this, it's fine, but you have to charge for that complexity that it took in reducing from that 6-dimensional representation down to that 1-dimensional representation. Okay? All right. Any questions about this? And so there's a word for this. Oh, I forgot the slide. You can't look at the data set and then use that data to determine what type of hypothesis you should craft, because essentially you're taking up the role of your learning algorithm. And with your learning algorithm, what it talks about is that when you make the decision, if that decision is made from the data, then you have to charge for that in terms of VC dimension. And so in deciding upon a model, don't examine the data, because you're effectively doing hypothesis selection, which is the job of the learning algorithm. And if you do that, you have to charge for that VC dimension when you're trying to do the analysis of complexity. Because if you do this, it's going to be bad for your out-of-sample error, because it might work well for this set of in-sample points when you go from this original 6-dimensional representation in your head down to this 1-dimensional representation, but it's not going to work out of sample very well. right? You're not really getting a VC dimension of size d tilde equals 1, or 1 plus 1 or 2 in this last step of our Z space representation. You're actually still paying the cost of this 6-dimensional representation, only you think that you're getting stuff for free. Okay, question? Ah, without examining the data. So if you have to examine the data, then you have to charge for the original VC dimension with the input that you're given, right? And so if you choose it and you choose a model without examining the data, because here we examine the data and we looked at it and we said, oh, wait a minute, I have an idea about its geometry. It's polar. So let me choose this transformation. And that's a good transformation, okay. But now you said, now looking at this transformation, I'm going to reduce it to this, and I'm going to reduce it to that. And so the cost that you really should pay is this VC dimension, not the VC dimension associated with this one-dimensional representation. So to answer your question, how you choose it is that when you're reducing these different representations, this reduction cannot be based on your examination of the data, right? And so here we actually visualized the data and we looked at it, we studied it, and we used what we understand about geometry to make a reduction to choose our new representation. And so when you do that, you're going to pay for it in terms of bad out of sample error. And so to address your question, how you choose it is either you don't look at the data, and you choose one, or if you do look at the data, know that you have to pay the original cost of the 6-dimensional representation that you originally had. Does that make sense? Okay. Any other questions? No? All right. So it's bad for your out of sample error. You can examine the problem, but you're going to have to charge for that VC dimension as a result of examining that problem. And there's a terminology for this. This is called data snooping, right? And if you data snoop, you're essentially, like a young child putting your hands in the cookie jar, right? You're taking cookies when you were not supposed to, and you have to charge for that if you want to truly represent the complexity of your problem. Because what will happen is when you get out of sample points, you're going to get out of sample points that are relative to the original representation. And it's just because you're doing this, it doesn't mean that you're going to eliminate that VC dimension associated with the original geometry. Okay? All right. So let's take a look at logistic regression. I'm going to do a time check. And logistic regression is another method for doing a nonlinear model. And so this is our friend, the linear model. And the linear model we saw W transpose X, which is essentially this. We augment our X vector with an X naught, and we augment our W vector with a W naught. And so we take the weighted sum, and this is sometimes called the signal S. And you can write it in sigma notation as follows. I goes from 0 to D of Wi xi. So it's essentially W transpose X. Now, when we did linear classification, we had two different labels. We had the +1 label and we had the -1 label. And so an arbitrary instantiation of a hypothesis was just some setting of those weight vectors, which have individual weight values, W0 up through and including WD. So for every value of our weight vector W, we have a particular hypothesis. And of course, how we got a class out of the hypothesis, we'd say the sign, is it positive or negative, of this signal, sign S or sign of W transpose X. Does that make sense? Now, schematically, how we're going to depict this is here we have our inputs in this stage. And these inputs, here's our X naught up through XD, and these are connected in through some signal lines here, and each one of those edges has a weight associated with it. So there's a W0 associated with the first edge, there's a W1 associated with the next edge, up through and including a WD is the weight associated with that last edge. And so each one of these comes in through a sum, and that's what this triangle represents. And we're calling that sum of all the weighted inputs is what we're calling our signal S. So that's just a schematic. And if it looks a little bit like a neural network, if you're familiar with neural networks, yeah, it's on purpose because PLA and perceptron is a neural network learning model that's implemented as a neural network, but you can certainly implement it as a function using W transpose X as we've done in the MATLAB on the assignments. And so here we have linear classification. And this outputs a +1 or -1 corresponding to the output of that particular instantiation of the weight vector, which is a given hypothesis drawn from among a set of hypotheses. So, excuse me, we also talked about linear regression. And linear regression is related to classification, only instead of looking at the sign of W transpose X, we're looking at the value of W transpose X, or the signal itself. Now, if we look at linear classification, we can think of sign as being what's called a hard threshold. And that hard threshold is represented as the function, and that function is computed on our signal, which is the weighted sum. Now that function says if it's positive, and you can imagine, origin is here, and you have positive values to the right, negative values to the left. If that signal is greater than 0, it's going to output a +1. If that signal is less than 0, it's going to output a -1. So we take the output signal and we input that to some kind of function. And in this case, for classification, it's what's called a hard threshold, right? Linear regression is different. We output this through, we can think of it as just identity function, right? If you input that signal, linear regression just outputs that signal directly. And so if we were to take that signal in the case of linear regression, again, we have the weighted sum of x0, x1, up through and included xd. We have each edge is also weighted similarly to how we discussed for linear classification, and we output that sum, s, our signal, we input that to a function, which is just identity, right? And so this function, if the value of s is 10, right, we can imagine origin here, we go 10 tick marks to the right, and the value is 10. Right? So it's just the identity function, which looks like a 45-degree sloping line that passes through origin. Any questions about this? Now, logistic regression looks like a mixture between the linear classification and linear regression. When it looks like linear classification, if we notice here, this is logistic regression, and the function that it uses is called the sigmoid, right? And sometimes it's called the so-called soft boundary. Now, when we go to the extremes, if our signal is very negative or the signal is very positive, you can imagine the set of coordinate axes here. If the signal is very positive, well, logistic regression outputs a 1, +1. So in that case, it looks a lot like linear classification. If the signal, S, the weighted sum of all of our inputs, is very high magnitude negative number, we go far out to the left, your left, then it outputs a -1 or something close to a -1. And in that regard, it's also acting like linear classification. But if you get closer and closer to 0, right, if our signal is closer and closer to 0, well, look what happens to this logistic regression. It kind of almost looks like it's this 45-degree sloping line. Right? So when you're close, the threshold, the signal is close to 0, it acts a lot like linear regression. When the signal input into this sigmoid function for logistic regression is far away from 0, it acts a lot like linear classification. So in essence, it's often called a soft threshold. And this is called a soft threshold because it acts like linear classification, the hard threshold, but if the value of the signal gets small, it's softer than this just +1, -1. Does that make sense? Okay, so here we have this logistic function, and this logistic function, or the sigmoid function, functionally it looks like this. It's e to the s, where s is the signal, over 1 upon 1 plus e to the s. If we divide numerator and denominator by e to the s, we get 1 over 1 plus e to the -s, which is the form of the sigmoid or logistic function that you often see in the literature. Now, this sigmoid function, or this logistic function, the range of this function is between 0 and 1 on the real number line. The domain is the set of all possible signals, so it's a real valued signal, weighted sum, but the range is between 0 and 1. So here, as we said, if your signal is a very high magnitude negative number, it acts a lot like a hard threshold classification. If it's a very large positive number, it's a +1. It acts a lot like a a linear classifier. It chooses one or the other, and you can scale it so it's +1 or -1. It doesn't really matter what the values are. But in between, if it's close to 0, it kind of looks like that regression, right? It's real valued line that's almost looks like identity. And so this value, the output, the range of this sigmoid function is between 0 and 1. It's called sigmoid because it kind of looks like an S that's been kind of rolled out and flattened a little bit. Now, because it's between 0 and 1, this form of hypothesis is often treated like a probability. A probability has a range whose values is between 0 and 1 inclusive on the real number line. And so oftentimes when we use logistic regression, we're essentially trying to learn a probabilistic function. And now what does that probability mean? Well, that probability is interpreted as being the probability of something having a +1 label, right? And we'll talk a little bit more about that in the subsequent slides. But nonetheless, one example you could use with logistic regression is perhaps you have descriptions of people like their age, cholesterol level, and a bunch of other factors you might measure for a patient over time. And then maybe you want to know the probability of someone having a heart attack. So you have historical records of a lot of patients with various metrics for the input features, age, cholesterol, etc. And then this signal, S, the weighted sum, you would call that a risk score, right? What's their risk? And you evaluate that with this soft boundary, the soft threshold sigmoid function, and you'd interpret that as a probability of heart attack. Does that make sense? Any questions about this? All right, let me check the time. 5:07. All right, so let me go for about 4 or 5 more minutes. I'll just stop on the next slide. Okay, so this hypothesis, our logistic function, our soft threshold of the weighted sum of our input vector is thought of as a probability. And recall when we talked about data, we said data can have so-called noisy labels. We have our label instance pairs, x and y, and these label values, +1 and -1, are governed by conditional probability. Probability of a plus label, y, given our input feature vector, x, or the probability of a -1 label, y, given our input feature vector, x. So as such, the ground truth target function, f of x, is the probability associated with a +1 label. And because of law of total probability, if we have 2 labels, then 1 minus f of x is going to be the probability for the converse, namely the minus label. So essentially, our target function, thought of as a probability, is going to be a real valued function, real valued in its domain over the set of feature instantiations, and its range is going to be a set of probabilities associated with the positive examples, those examples that have a +1 label. And so in essence, what we're trying to do, we have our final best hypothesis. It's going to be sigma or theta. Well, I have theta here, but I don't know why I said theta, probably because it was easier to type in the equation editor than sigma. So we have our final best hypothesis is going to be some weight vector such that sigma of w transpose x is roughly equivalent to f of x. And what are we trying to do? Well, we have these ground truth target labels, ground truth class labels assigned by the target function, and there's a probability that we're going to associate a plus label with a particular instantiation of our feature vector x, and there's another probability that we're going to associate a -1 label. So essentially what we're trying to do here with our logistic function is we're trying to find a linear model, linear in W, our weight vector, such that we can best mimic the probabilistic assignment of +1 labels and -1 labels to input feature vectors. Does that make sense? Okay. Any questions about this? Okay, so I'm going to stop here. It is now 5:09, and that gives us 35 minutes to go over any questions you might have about the material. And so if there are no questions about this particular, what I'll do is I'll end here and open it up for general questions about any and all the material that we have thus far.